To wrap up the use of the 2D static model, I want to cover the outputs and how you would interpret them to decide, is the job too stressful, does it need to be redesigned, or is it well within human capabilities that we don't expect to see an injury in it. So starting out with the ErgoWeb screen, the input screen, I've entered some of that same information. For example, from our last problem where the practice problem using the protractor, I've input those angles to show you what the person looks like. From the screen, once you get everything entered, again, you're ignoring hand location, ignoring positioning mode. Don't need to do anything with those. You're going to click Submit. Submit, it will give you a little bit of information here. It will give you data inputs, and so it's going to show you what you entered on the previous screen so you can confirm that. Then it's going to give you calculations, and I'll usually refer to those as outputs that we're wanting to interpret. It gives you a back compressive force, a shear force, and then required moment of torque at each of the joints we've looked at, a percent capable, and then gives you some conclusions and makes some recommendations about potential task modifications that would improve the job. Okay, so we're looking at those. I'm going to go back to my PowerPoint to step you through some of those things. The first thing, when material handling, usually the item of interest will be your low back. We're trying to prevent low back injury. This model will prevent injury, make recommendations to prevent injury to the disc, so the intervertebral disc at L5-S1. And so that's probably the most important factor you're going to consider. The low back compression, I'll interchangeably call it stress on your lower back, or compressive force, F sub C, on your back at the L5-S1 joint. Those just mean, again, lower back stress, lower back force. The model calculations will give you back compressive force. For example, if ErgoWeb gave you an 1,162 pounds, that sounds horrendous. It gives you a color-coded dot, either a red, green, or yellow, as an indicator of how bad it is. But the interpretation on that is, if we want to prevent low back injury, we want to limit this compressive force to a value less than or equal to 770 pounds. And so previous studies have cut out spinal sections of cadavers. They loaded them up so they can compress them. They were looking for failure. When does a cadaver spinal section failure? They found that, well, these were relatively safe, did not fail at limits lower than 770 pounds. And I've given you the metric here too, if you're interested in metric. And so on a job that, if the compressive force is less than or equal to 770 pounds, I would say that's an okay job, no need for redesign. It's a low risk job. We don't expect to see injuries in it. And we can see by my example, my example here on screen has a compressive force of 1,162 pounds. That's greater than 770, and so there's a problem there. We might see injuries in this job. So you'd want to go back and redesign it to either improve the posture or reduce the loading on the hands, the weight that's being lifted. Okay, so that's one thing that we want to consider. Another thing to consider is a shear force. If compression is up down, shear is sideways. So a sideways force, a backwards and forwards force. ErgoWeb will give you that calculation as a shear force, and in my example here is 107 pounds of backwards forwards. If we want to try to prevent injury, we want a shear force less than or equal to 225 pounds. And so in this case, we don't expect to have an injury to our L5-S1 intervertebral disc, since the force is lower than 225 pounds of shear. Okay, so compression is a problem, shear is not. Okay, so far we have a bad job that we would need to fix in my example. The remaining, and looking at the moments or torque, ErgoWeb gives you the torque at each joint, so the moment at each joint. These are the moments that your muscles crossing the joints, so all the muscles crossing each joint would have to produce in order to to perform this job capably without injury. So it does give you the calculation for moment of torque, for example, 389 pound-inches of flexion. So your elbow has to flex with 389 pound-inches. They're using, instead of pound-feet, the numbers are smaller, so they're using pound-inches. That's not as meaningful as the next step. It also gives you that 90% of people are capable of producing the 389 pound-inches of flexion. 90% as well, it's a good proportion of the population. Good proportion of the population that can do the job, that are capable of doing the job. And so to interpret the moments required, the strength moments required, we're instead going to look at the percent of the population that's capable. To prevent bodily injury, we want to design so that strength limits are not exceeded at any joint of the body. Okay, so we have to look at each joint in turn. Our design goal, what we're trying to get, is to have percent capable greater than or equal to 75% at each and every joint. So all the joints percent capable are greater than 75%. If they are, then at least 75% of our workers, of our employees, have the strength to do this job without an increased likelihood of injury. Okay, so 75% is our design goal. If any joint is less than 75%, that means that we don't have that we would expect to see injuries, because some people don't have the strength capability to do the job without injury. They just don't have the strength to do it. And so in turn, we would go down to each joint successfully and see, does it have the strength? In our elbows, 90% is greater than 75, so we're good. Shoulders, 68%, so no, we don't have the shoulder strength. This is a problem job. Our L5S1, we have the extensor strength of our extensor muscles in our spine are capable. Our hips good, is above 75%, knees good at 92%, ankles good at 99%, but this is a problem job at the shoulder. We expect to see some shoulder injuries in this job. This lowest joint percentage is our weakest link, or our limiting joint, and so out of all these joints, I would say the weakest joint, the limiting joint, is the shoulder. It is the weakest link in our body. In this position, in this posture, on this particular job, this is the joint that we expect to see injuries. So the shoulder would be the problem in this job. So for a final interpretation, we saw that when we looked at compressive force on our back, it was too high. We expect to see some back injuries. We can see that our shear force in our back was not a problem. Don't expect to see injuries due to shear force. But we also see that our shoulder is a problem. We expect to see some shoulder injuries. Okay, so low back compression and shoulder strength requirements are too high. Okay, so that was our interpretation of the problem. The homework has several problems where you're interpreting the same information. But before I leave, I just wanted to give you some cautions about biomechanics. First of all, the two-dimensional static model was groundbreaking at the time, back in the 1970s or 80s, whenever these were first developed. This was one way we could estimate how some of the effects due to forces and moments on our body. But it is rudimentary. It only will look at an instant at a time. The instant in time you want to pick within an entire lift, entire dynamic lift, is the most stressful. And so usually you're looking at that first initial posture when you're just about to lift the load. So right at that instant in time, you take a picture of it, you analyze a single frame. But you can also analyze the end of the lift as potentially being the most stressful if they're in a particularly awkward posture, if they're reaching too far. Everywhere in the center, if you were videotaping it, all those frames in the center, you typically ignore those as those aren't the most stressful. Those are usually less stressful. Rudimentary, as in it'll only look at an instant in time, that one single frame. It doesn't care about the age of the worker. It doesn't care if the worker's been injured, has a previous injury before. Both of those factors we know will make a person more susceptible to injury. So this particular model doesn't care. It also doesn't care about the work shift. If you're on mornings, evenings, afternoon, it doesn't care the time of the shift. If you're just starting out fresh or if you have fatigue effects at the end of the day, it just does not account for that. We also know there are some inaccuracies. I'd mentioned we either look at the beginning of the lift or the very end of the lift. So beginning or end as being most stressful. Those are the best that we can pick. But if you were able to track what's happening at each instant in time throughout an entire lift, we can see that the force on your back actually increases up to a peak within 0.3 seconds or so within a total lift. Okay? There's no way for us to capture that point in time to be able to identify that, and so the best we do is this start the beginning or the very end. Okay, so we know that we're underestimating the stress. And then also caution, as I mentioned at the beginning, there are different types of biomechanicals out there. This model we're using looks in particular at potential for back injuries because, well, that's been the most expensive injury that the workforce has experienced. Within the back injuries, ErgoWeb has a shoulder. I shouldn't say within a back injury model, but it does have a function. It has a tool that will let you look at shoulder moments in particular if you've got shoulder injuries instead of back injuries in your job. I've mentioned the 2D versus the 3D issue. For example, this particular biomechanical model won't let you look at if a person twists their trunk. It will look at very limited twisting. It doesn't allow for it. So it's a two-dimensional. If you have extreme twisting, you would want to switch to a three-dimensional model. Also, it looks at static points in time rather than dynamic lifts, and that caused our problem over here about we know there are errors present here. The wrist carpal tunnel syndromes are more recent concerns, so there aren't quite as many models. In fact, this particular model, it lumps your hand wrist into your lower arm segment, and so it doesn't let you estimate what's happening at your wrist. And so you might have run across, ErgoWeb doesn't have it, but you might run across a wrist model, biomechanical wrist model. Okay, with that, there is a homework assignment. So there's a homework set. The homework set also includes an article on the role of physical ergonomics in litigation. It does tie in the use of biomechanics in litigation issues, so I thought that would be a good tie-in to this week's homework set. Do the homework, understand the homework before you take the quiz, and then there's a practical application. I want you to go ahead and use this 2D biomechanical model in your workplace. If you can't use your workplace, then analyze a task at home. Okay, so that concludes this week's lecture.